Good evening to your audience, and thank you for the opportunity to make a presentation here. So in my today's talk, I'm going to take you on a journey to our closest neighbor, the incredible moon. In particular, I'll tell you about lunar meteorites as one of the attractive ways to study the moon. I will give you a brief overview of the structure of the moon's surface and tell you about all of the lunar sample return missions. We will also discuss their main drawbacks and get right down to the talk about lunar meteorites, a method of studying the moon without having to fly to it. We will talk about what they are, where we can find them, their numbers, and the most interesting thing from my point of view is the information that we can get about the moon by studying lunar meteorites. So let's start. Have you ever noticed that the moon has uneven color in different regions? There are two different types of the moon surface. We have white areas known as highlands, representing an ancient lunar crust, which consists mainly of rock called anorthosite. And we also have dark areas known as mare basals. They referred to be seas by early astronomers, but now it is known as the fact that it is large lava fields. The heyday of the lunar exploration occurred in the 70s of the last century. We all remember the American Apollo missions with astronauts and the Soviet lunar missions with robotic explorers. 44 years later, Chinese Chang'e 5 lunar mission successfully brought back pristine moon rocks to the Earth. So, up to date, we have 3 countries with lunar sample return missions and 393 kilograms of moon soil. On the slide, you can see photos of these returned rocks, anorthosite from Apollo 16 and the basaltic soil fragment from Apollo 15. Unfortunately, lunar expeditions have some significant shortcomings. As you can see, all missions that have returned rocks only from the near side of the moon. They shown on the map with flags. It follows that these samples from these missions have provided only a limited understanding of the origin and evolution of the moon. Besides, the moon demonstrates a global compositional asymmetry. For example, all samples from the Apollo missions contain abnormal concentration of the radioactive element thorium, which is not typical to the entire surface of the moon. It is concentrated in a certain area called as Procellarum KREEP terrain. That's why we need a new source of lunar matter, and where we can find it. Just then, lunar meteorites come to the rescue. In the common language, they are pieces of the moon that we actually find here on Earth. The history of the lunar meteorites formation is shown on the left. At the beginning, an asteroid or a comet impacts the moon and ejects the lunar material. Then, a lunar rock is accelerated to escape velocity and leaves the moon's gravitational field. It travels on a relatively short distance and eventually lands on Earth. Someone finds it and someone recognizes that it's from the moon. Simple as that. The idea that meteorites could be ejected from the moon is not particularly new, but there was the lack of evidence until the discovery of Allen Hills, the first rock recognized to be a lunar meteorite over 7 years after the last lunar mission. And the study of lunar meteorites is very important as they are likely to represent a more randomly distributed locations of the lunar surface from both sides of the moon. They also show typical to the moon low concentrations of radioactive thorium. And where we can find them? Perfect places to hunt for meteorites include hot and cold deserts where rocks of terrestrial origin are rare. To this day, we know 649 lunar meteorites, and their number just keeps growing. Their mass has also nearly doubled the mass of lunar missions. Nevertheless, lunar meteorites are very rare rocks. Only 1 out of 1,000 is truly from the moon. And what information can we learn from lunar meteorites? I will try to reply to this question using my own research as an example. This is the second year I've been working in the laboratory of meteoritics and cosmic chemistry where I study lunar meteorites. One of them is NVA 11828. This abbreviation means Northwest Africa, the desert where it was found in 2017. NVA is a lunar breccia, a type of rock containing many different lytic fragments brought together by impact processes. And in my research, I have studied a polar spin section as on the picture above using methods of optical and electron microscopes and the science from the lunar meteorite. Based on the texture of rocks and their chemical composition, several types were carried out. On the slide, you can see the map of this spin section, and different types are outlined in different colors. And as you can see, the meteorite is dominated by fragments of typical highland rocks. They are shown in green. But rare fragments of mare basalts and the creepy rock are also found. They are shown, they are highlighted in red and yellow boxes. So we can make a following conclusion. Presumably, the meteorite in the 11828 could be ejected from the highland region of the lunar near side, where these rocks are widespread. And the conclusion of the whole speech. The study of lunar meteorites has a number of advantages over lunar return mission samples. I haven't talked about it, but I think it's quite obvious. Lunar meteorites are under your feet, free and in touch. The second point is random nature of ejecting. It means that they can be in equal measure be either from the near side of the moon or from the far side. The third is a more complete representative reflection, the composition of the lunar crust compared with samples by the Apollo missions. And by studying lunar meteorites, we can get information about the origin and evolution of a terrestrial body, including our planet the Earth. So that's all. Thank you for your attention.